Welcome to this screencast on calculating probability. We're looking at compound independent events today. So a compound event means that there are two or more events that are being combined to create an outcome. And the fact that they're independent means that the two events do not affect one another. For example, if you are going to roll two dice, then the one does not affect the other. Or if you are going to choose something out of a bag, like a marble out of a bag, you would have to put the marble back in before you chose a second time. So this would be choosing twice with replacement. But this is where the two events do not affect one another. So I want to remind you that one way to come up with all the different possible outcomes for theoretical probability is to create a tree diagram. And tree diagrams are simple and easy, except they can get really cumbersome and really large. So we want to have a different way of coming up with the total outcomes besides that. And we did talk about if there are two choices for the first event and two choices for the second event, and then there's three choices for the third event, then to find the total number of outcomes, you would multiply 2 times 2 times 3. So for this situation, when you're choosing lunch, there should be 12 total outcomes because you multiply 2 times 2 times 3. So you can multiply the different outcomes in each event to find the total outcome. So just to make a point, try drawing a tree diagram of all the possible outcomes when you roll two dice. Getting it started, I'll just get you started at the start. You're going to roll one die. So at the start, we're going to roll one die, and there will be 6 outcomes. And then we roll the second die. For each thing we landed on the first time, there will be 6 more outcomes for each of the 6. So for each of these things, I would have 1, 2, 3, 4, 5, 6 lines coming off. And I would do that for all 6 of these. So you can see my tree diagram get really spread out, and it can be kind of cumbersome. But we know if there's 6 choices for the first die, and there's 6 choices for the second, then the total number of outcomes when we roll it twice, or roll 2 dice, should be 36 total outcomes. So when we make our tree diagram, we're going to have 36 things coming off the tree. And that gets really confusing. So there's a shortcut to finding, just like there's a shortcut to finding the total number of outcomes, there's a shortcut to finding probability. Now, at this point, to find theoretical probability, we made an organized list to come up with all the different possible outcomes. Another way we did it was to make a tree diagram. What we also found, to find the total, we can multiply. So we're going to use that concept to help us calculate the actual probability. We're going to use multiplication. So for example, if you're trying to figure out what's the probability of flipping 2 tails. So you flip a coin twice and you get tails both times. Well, the first time you flip it, the probability of getting tails would be 1/2. The second time you flip the coin, the probability of tails is still 1/2. So the probability of getting tails and tails again would be 1/4. And if you think about it, if I listed all the outcomes, there would be 4 outcomes: heads, 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 tails, tails, heads, and tails, tails. So only one of those 4 would be tails twice. So I can either list the outcomes and then see it's 1 out of 4, or I could have just multiplied 1/2 times 1/2 to get 1/4. Let me show you on a different example how that works. Here are the different situations that this would work for. This would work great. Multiplication works great when you're doing 2 events that do not affect one another, and also where you're looking for this and this to happen, like flipping a coin and getting heads and rolling a 6 on a die, or spinning a spinner and landing on green and pulling a card from a deck and getting a jack. Like when the 2 things don't affect each other, and you don't have to, and you want this and that to happen. So if we did a problem like this, a bag contains 3 red marbles and 4 white marbles. So you're going to choose a marble out of this bag, and then you're going to choose again. So you're going to choose a marble out of the bag, you're going to put that marble back in, and then you're going to choose again. So the first time you're going to pull it out, look at it, see what color it is, then put it back in, and then choose a second time. So what's the probability you will choose a red marble both times? Now, one way to get that would be to create a tree diagram. But if you create a tree diagram for this, remember there's 7 things in this bag, because I can't just say red and white. I need to list all 3 red and all 4 white because they're not equally likely. So there's 7 things in this bag, and there's 7 in this bag. So if I found a tree diagram, there's going to be 49 total outcomes. That's going to be really ugly. That's going to be a really ugly tree diagram. It's really complicated. But let's try this more easily. If I want to see if I can choose a red twice, then the first time I put my hand in this bag, I have 1, 2, 3. I have a 3 out of 7 chance of choosing a red marble. If I put that red marble back in, shake it up, and choose again, I still have, the second time, a 3 out of 7 chance of choosing red again. So that means in those 2 out of the 49 different combinations of marbles, 9 out of those 49 are going to be red. Now, if you don't believe me and you want to prove it, go ahead and pause this and draw a tree diagram, and you'll see that out of the 49 outcomes, 9 of them are red. So when we're rolling 2 dice, how many different outcomes can we get? We said before, 6 on the first die, 6 on the second. That means there's 36 total outcomes. So then what's the probability that both of them will be odd? Well, on the first die, 3 out of 6 of the numbers are odd. So the first time I roll it, I have a 3 in 6 chance. The second time I roll a die, how many of them are odd? Still 3 out of 6. So for me to get odd and then odd again, that would be 9 out of 36. Things like 1, 1, 1, 3, 1, 5, 3, 3, 3, 1, 3, 5, 5, 1, 5, 3, 5, 5. Those are the 9 different possibilities. This spinner is not equal, so you have to be careful when you're calculating the probability. But if I want to know what's the probability if I spin this spinner twice, if the first time I'm going to land on yellow and the second time I'll land on green. Well, let's look at green. What fraction of this spinner is green? 1/4. What fraction of it is yellow? Well, some people want to say 1/5, but you notice that there aren't 5 equal size spaces here. So even though there's 5 colors, they're not all equally likely. The yellow takes up half of what the green does. So I would have to divide this spinner up into equal size pieces. So now I see that, blue on blue, there's actually 8 sections in this spinner, and 1 out of 8 of them are yellow. So then what's the probability that I'm going to land on yellow first and green second? It's 1 out of 32. So let's try this one. Now this spinner has 5 equal size slices, and then we're going to roll a die. So what's the probability I'm going to get green on the spinner and an odd number on the die? Well, green, only 1 of these 5 are green. And how many numbers on the die are odd? 3 out of 6. So the probability is, that's right, 1/10. Now you might say, wait, Mrs. Bowers, that was 3/30. Well, I simplified it, so it's 1/10 or 10%. What's the probability of getting 2 5s? Well, since there's a 1 in 5 chance of getting 5 on the spinner and a 1 in 6 chance of getting 5 on the die, they have to multiply them. 1/5 times 1/6 is 1/30. So what's the probability of getting prime and then not prime? So prime on the spinner and not prime on the die. So a prime number only has exactly 2 factors. So the prime numbers on the spinner would be 2, 3, and 5. 1's not prime because it has exactly 1 factor. And 4 is not prime because it has 3 factors, 1, 4, and 2. So 2, 3, and 5 are the prime numbers. And that's the same prime numbers that are on a die, because 1 is not prime and 6 isn't prime either, and neither is 4. So I just multiply those together. 3 times 3 is 9. This would be 9/30 or 3/10. The probability of getting prime and then not prime, there's 3 that are prime and 3 that are not prime. So prime and then not prime would be 3/10 or 30%. So in conclusion, just remember that if you're going to be finding the probability of this and this, so if there's 2 things you're finding, like you're going to flip a coin and roll a die, and what's the probability of heads and 6, then you multiply those 2 probabilities together of each event, and that will give you the theoretical probability. Okay, thanks. Hope you enjoy the shortcut. Make sure you practice.